In this video, we begin our discussion of the actor model of parallelism. The actor model actually has a long history. It was created in the early 1970s by Carl Hewitt, but it didn't get much attention at the time, mainly because computers were generally not very parallel. And the actor model excels at giving us the ability to do operations in parallel without having a lot of the problems that come with low-level multithreading. The way the actor model works is you have actors, which are kind of like objects that have threads attached to them. Now, in reality, there isn't one thread for every object or for every actor, because you could have many thousands of actors and you don't want to create many thousands of threads, but it's a good mental model for how you think about things. Instead of calling methods on your actors, you give them messages, and each one of your actors has an inbox, and that inbox acts as a queue. The first message that's received is going to be the first one that's processed. Now, to understand this, I want to look, this is called a sequence diagram. It's a different type of UML diagram. And this is using the standard approach of calling methods. So at the top here we have three different objects, A, B, and C. And vertically we have a time axis. And so this is kind of a timeline for each one of these objects. So at a certain point, A makes a call to B. It calls the foo method on B, and that method goes for a while, and then it returns. Now in this image, I'm assuming that we have a multi-threaded program here. So while A is processing, at the same time some stuff is happening over on B, or over on C, and C makes a call to B, and it calls a method bar. What happens in this region in between here is that we have two threads. So the threads are basically going back and forth between objects. And that's what happens when you make normal method calls, is that the threads jump around between objects. And the challenging space is right here, because if foo and bar both mutate data inside of B, then it's possible that they're mutating the same data and we have a race condition. Actors get you away from this, because with actors, each actor, instead of having the thread go across, the actor sends a message and it keeps working on its own thread. And also actors only process one message at a time. So that same diagram might look something like this. So A would send a message of foo over to B, and then B would work on that. Now while B is working on that message, C sends a message of bar, but that message just sits in an inbox until B is done with whatever work it got from A. And then after it has finished the work from A, it can go ahead and process. And you can see fairly clearly here, there's no possibility for a race condition. All the mutations in B are happening in one thread. So basically A, B, and C, inside of this timeline, there can only be one thread operating there at a time. Whereas with normal method invocations, every thread in your system could wind up being operating inside of a single object. And so this is how the actor model helps you get around things. And we just have to follow a few simple rules. One of the big ones is that if you have mutable data, it stays inside of an actor. So actor A can have mutable data, B can have mutable data, C can have mutable data, but they don't share them. So I never send a message that contains mutable data. My messages will be immutable, and that way B can mess with its own mutable data all at once, and neither A nor C will ever touch it, and everything remains happy. We'll typically make these messages in Scala using case classes, because case classes are a really nice way to make small immutable data structures, and also they will have the advantage that they do pattern matching. And so we'll see how that comes into play in the following videos.